Hello everyone, I welcome you all to Part 12 of Python programming series. This is Ram Prasad Pujari. In this session, we are going to talk about performance metrics used for regression algorithms, and we're going to have discussion about three important metrics: mean square error, mean absolute error, and R-squared score. In the previous video, that is part 11, we saw how a linear regression model is trained using a fit function of scikit-learn. Once the model is trained, then it becomes necessary to evaluate the performance on a new data set, that is the data set which is not part of training data set. So we already split the original data set into training data set and test data set. Training data set, which has 80% of the samples, are used for training the model, and remaining 20% of the data set is used for evaluation. So today we will see how a model after the training is evaluated. So here, in order to evaluate a model, we need a performance matrix. Now, type of performance matrix depends on the machine learning model that we have. For regression models, mean squared error, mean absolute error, and R-squared values are used. And similarly, the classification models will have a different performance matrix, so that we will discuss in the next session. The first, we need to import necessary libraries. Now for this task, we need pandas library, as we are going to use advertising data set, which is a CSV file. So then we need to import linear regression model, and which we have already seen in the last session. And the new thing is we also have to import the performance matrix, MSE, R2 score, and mean absolute error. So these functions are to be imported from metrics module of scikit-learn. So then we have a train test split function of scikit-learn. So these are the necessary libraries that we have already imported, and again we are going to use advertising data set here, which has 200 rows and 3 features and continuous value as a target variable. So this we have seen in the last session, and we are going to use a train test split function. So we have already used a train test split function in the last session. So this will divide the original data set into 2 different data set with the ratio of 80:20, 80% for the training data set, whose x value is called as x train, and y value is referred to as y train. And similarly, x test and y test are the labeled data set for the test data set. And in this case, the test data set will have 40 rows or 40 samples, which is 20% of the original data set. In the last session, we have seen when you train a model using a fit function, we input x train and y train. That means x train along with the label, and that will give us the model parameters, which are nothing but coefficients and intercept. And once the model is trained, then we get this beta naught, beta 1, beta 2, beta 3 parameters, and fit function is used. And once the model is trained, after that we need to evaluate the model on a new data set. So we have a test data set. We have x test and y test values, where y test is the actual value of the test data set. Now in order to evaluate the model, the first thing is we need to get the predicted values for the test data set. So what we do is we have a trained model here. The trained model is one whose parameters are already known or computed. So we input x test, and then we obtain the predicted y values. So there are 40 values, and predict function is used to perform prediction. So this is our model which is already trained, and model.predict is used for performing predictions. So we input x test, and that will give us the predicted values, and this will have a 40 values or 40 y values, which are displayed here. As you can see here, these are the 40 predicted values by the model when we input x test. Now y test is nothing but the actual y value of the test data set, which are shown here. I have taken a transpose of it. Now once we have the predicted values for the test data set and the actual values, we can perform evaluation. So we can compute the error between the actual values of the test data set, actual y values, and the predicted values. Now for this we use some performance metrics, and one of them is MSE. Now this is the formula for MSE, and MSE stands for mean square error. So we compute the average of sum of squared errors, and very simple example is shown here that will explain us how MSE is obtained. And since it is an error, ideally we expect the error to be equal to 0. So lower mean square error indicates that the predicted y values are closer to the actual values. Now we can compute the mean squared error using a function called mean squared error, and these are the input parameters, y test and y predicted. Y test is the actual y values of the test data set, and y predicted is the predicted y values we got when we used the predict function, and it shows that the error is 3.17. So there is another performance matrix called as mean absolute error. So where instead of squaring the error, we take the absolute value of this and then we compute. The procedure remains the same, except that instead of squaring the error, we take the absolute difference between the y test and y predicted values. Now in this case we get 1.46. As we know that MSE will be always larger because you are going to square the difference between y test and y predicted values, whereas in this case we take the absolute value, so hence MSE will be always larger. The range for mean absolute error and mean squared error will be from 0 to positive infinity, because MAE and MSE values cannot be negative, and the minimum values that we expect is 0. And if the mean absolute error or mean squared error is 0, that indicates that the model perfectly fits to the data, or it indicates that predicted values are perfectly, so they match with the actual values. So this is what they indicate. But if you look at the range, it is from 0 to positive infinity. Now in order to overcome this, we have another performance metric which is called as R squared value, and this is the formula for R squared value. And R squared value will give us straightforward interpretation, because the value range between 0 and 1, where 1 indicates absolute fit, that means model correctly fits to the data, and 0 indicates that model does not fit to the data at all. And so this is how it is calculated. And so there is a function called R2 score, which we have already imported. So you can input y test and y predicted values, and that will give us the R square value. In this case it is 0.85, which shows that 85% accuracy. So any value that is close to 1 indicates a better fit, and if the value is closer to 0 indicates the model does not fit to the data. So this is how we calculate R squared value, and this is the formula. And so here one is the predicted value, other one is the actual values. So let us compute all the three scores together. The first one is MSE, and mean squared error function is used here. Y test and Y predicted values are the input parameters. So I am printing the mean square error. And similarly, the second performance metric is mean absolute error. Again, the same inputs are fed. So this is the actual Y value and the predicted values when I used model.predict function. And this is the R2 score. Now all these scores are calculated for the test data set with 40 samples, and you can see that MSE is around 3.17, mean absolute error is 1.46, and R2 score is around 0.89, which is very close to 0.9. So as we know that R2 score ranges between 0 and 1. So 0.899 indicates that model fits correctly to the data. Now this particular computation we carried out for the test data set. It is also important to calculate the error for the training data set, because we have trained the model by giving X train and Y train together. We use a labeled data set, and if you look at this, so in order to train a model, we fed X train and Y train, and we got the model parameters. Now once the model parameters are computed, and after that in place of X test, so we can give X train and we can perform prediction on this. So we can get the predicted values for the training data set as well, and we want to compute the accuracy for the training data set as well. So the same way we can repeat this procedure. The first we apply this model.predict function. Now the input is X train and we get the predicted values. We already have the actual values, which are nothing but Y train. So now we compute the mean square error, mean absolute error, and R2 score by using these functions. And you can see that the error is 2.7 in this case. It is slightly lesser than the test data set. So which shows that the model performs well on training data set as well as the test data set. So sometimes what happens is model does not perform well on the training data set itself, which indicates underfitting. And we will discuss about underfitting, overfitting in a separate session, so not today. So this session is about the performance matrix, and I have introduced you to 3 performance matrix which are used for regression algorithm. With this, we will wind up this session. Thank you.